Good day, everybody. As we start this new section 2.4, we're going to attempt a couple of warm-up problems first as we look at the main objectives. The objective of 2.4 is to study what's called the chain rule. And the chain rule is a general differentiation principle that applies to any function that can be thought of as a composition of two functions. And during the warm-up problem today, we're going to review what a composition is, how to construct a composition, and how to deconstruct a composition. It's really important in the decomposition or deconstruction part to see how that's done so you can apply what we're going to call the chain rule. And so our main objective in this video is going to be to talk about objective number 1. See what the chain rule is and see a specific application of it, and that's going to be called the general power rule. So our warm-up problem, there's actually two. One is to take two functions, one called f of x, one called g of x, and to do two compositions. One would be what's called f of g of x, and then I'm going to flip it around and construct g of f of x. So the first one says take function f and insert into it function g. So I look first at f. F of x is squaring something, x. But I want to take it and make f of g of x. So on one side, f of g of x would be to take whatever f does, which is whatever the input is squared, but this time the input needs to be g of x, which would be the expression 3x plus 1. So without any further simplifying, this would show the construction of f of g of x. Take g of x and then square it, because that's what f is supposed to do. Now the other side is that we want g of f of x. So g is applied to f of x. G takes the number x and multiplies it by 3, and then adds 1. So this time, what we're going to put in there for the blank is what f of x is, which is x squared. Now this one could easily be written without parentheses, so I could write 3x squared plus 1. Final answer. So now it's really important, though, that if I give you a composition, you be able to decompose it into basic functions. So if we were in class here, what we would have done is about 3 or 4 versions of this, because when you decompose a composition, there's always multiple ways. Okay, in fact, I could come up with hundreds of ways to do this, but let's look at a couple. If I give you that the square root of 5x squared plus 2 is called f of g of x, what I'd like to do is come up with what could have been f and g. Okay, I'm going to come up with a couple. I encourage you to think about it on your own too. Maybe even just pause the video now and see if you could come up with a couple of different ways that you could express f of x and g of x, as I try and do a couple myself here. Okay, well, one way would be, I think I could let g of x be x squared, and then that would mean f of x could be written as the square root of 5x plus 2. I notice that would work because if I think of the original problem as f of g of x, that means in f of x, wherever x is, I would now replace it with x squared. And so now it would be 5x squared plus 2 when I compose f of g. So this is for sure one way to do it. Another way would be to just call the entire inside of the root g of x 5x squared plus 2, and then f of x would simply be the square root of x. And so now f of g of x would also produce the square root of 5x squared plus 2. Let's see if we can come up with one other way here. Oh, how about this one? If I let g of x be 5x squared, and then f of x could be just x plus 2. That for sure is a third way. Okay? Now, all three are valid breakdowns of f of g of x. All three of these, when combined, in that way would produce the square root of 5x squared plus 2. Now, and I could come up with probably a dozen other ones, but there's one of these that for the purposes of calculus and derivatives is the best one. The best one is the one where if I asked you what is f prime and g prime, both of those derivatives would involve just basic techniques that you've already learned. So I encourage you to look over the three options we have, and which one do you see where f of x and g of x both have derivatives that you could find right now? And I'm hoping you're looking at the one in the upper right corner. Okay, because if this is the decomposition I've picked, f prime of x would be the derivative of the square root x. We've already learned that, or we can apply the power rule. G prime of x is a simple derivative also. There's a simple polynomial. The derivative of g would be 10x plus 0. Okay, so for the purposes of using the chain rule today and finding the derivative of this composition, this is the winning combination right here, because we want to break it down into two functions whose differentiation rules we already know. Okay? So let me show you a couple other instances where I have a basic derivative on the right, one we already know the answer to, and a similar but more complex version over here. Okay, so we know how to find the derivative of x to the 12th. Here I've got a slightly modified one. It's not just x to the 12th, it's x plus 4 to the 12th. And so this derivative, to do it correctly, would be one of two ways. Either expand this all entirely out into a really, really long polynomial, or today we learned the chain rule that will make that a one-line answer. Okay? Here I've got the derivative of sine x. We know that is cosine x. Here it's slightly more complex. It's not the sine of x, it's the sine of root x. And over here I've got derivative of e to the x, which we know the rule for that. Here it's slightly modified as e to the power x cubed. So this would require us to know the chain rule if I wanted to find this one's derivative. Before we look at the chain rule again for the first time, let's just practice decomposing one more time. The three functions on the left are compositions, and I want you to think of them as f of g of x. This time, when I write g of x, I'm going to use the label u. And when I write function f, I'm going to use the label y, but I'm going to make the variable u. And you'll see what I mean here in the first one. If g of x is supposed to be the innermost part of the composition, I'm going to let that be x plus 1. But I'm going to use the label u. So u is x plus 1. And on the other part, y would be 1 over u to the 5th. So you notice that this leads to a direct substitution. If I let u be replaced with x plus 1, this leads to the original problem or original function y equals 1 over x plus 1 to the 5th. Let's try this. Let's try breaking the other two down in the same way. I could let in the second one y equal the square root of u, and then I would let u equal the quantity 3x plus 2. So now directly substituting first column into the second one, I would get the original expression. For the third one, you have to be careful. Sine squared x is a synonym for sine x all squared. So I would let y be the squaring function, y equals u squared, and then I would let u be sine x. Okay, knowing how to break these down in this way is important, because what I want you to notice is the derivative of the right column, the derivatives of the expressions on the right are all basic derivatives. They all can be done with the power rule. Okay, this one can be written as u to the minus 5. This one could be written as u to the 1/2. And this one already is u to the power. So the derivatives of the three expressions on the right all are just would be involving the power rule. Okay, this is very important as we try and work through today applying the derivatives of the expressions on the left. Okay, it's very important that you be able to decompose them in this way.